Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, we're going to get started. This morning I'm pleased to introduce Alexander Tarvo, who's visiting us from Brown and has a background also, before he started at Brown, he was in Windows. So he's got a bit of an engineering background as well. And he's going to be telling us this morning about some work he's been doing on automated performance modeling of multi-threaded programs and related work.
Good morning. Can you hear me? Yes. Thank you very much for this opportunity to talk here. So I'm going to present my thesis work, and this is about automatic performance modeling of multi-threaded programs. So in fact, during my work, what I did, so I developed an approach, a model specifically aimed to simulate multi-threaded programs, and methodology to build these models automatically for large complex programs like Sunflow, for example. It's a 3D renderer, an industrial program, and Tomcat, which is Apache web server. So we developed this methodology and we verified it with a set of large industrial applications. So this is a brief agenda of my talks. First of all, I'm going to talk a little bit about motivation of this work. I briefly touch approaches, existing approaches for performance modeling. I'll talk about definition and structure of our model. Then I will tell you how we build those models automatically. And finally, I will present you some results about evaluation of our model. So the motivation here is simple. Understanding performance of multi-threaded programs is a really hard problem. These programs, they engage in synchronization and locking activity. Some sections of their code might run in parallel. Some sections, they might run in not in parallel, like it's a single-threaded code. And these programs, they utilize resources of the computer concurrently. Like they concurrently use CPU, hard drive, network. And as a result, the performance of these programs is going to be really hard to understand. Strictly speaking, there's going to be a very complex dependency, nonlinear dependency between the configuration of these programs and their performance. Here, under the configuration, I mean both characteristics of the hardware where the program is deployed upon, the program configuration options itself, like the number of working threads for a program, or the size of the internal queue. As one of the parameters of the program configuration is the workload parameters. Like if you have a web server, how many requests per second the web server gonna take. So all these parameters, they constitute the configuration of the program. Just to give you an example, let's suppose that you are trying to deploy a web server. Suppose that this is a simple case, a web server is gonna serve a request to static web pages, and you are wondering how many working threads you should have for that web server, how you should configure it, or how many requests per second the server should receive from your load balancer. Because if you're gonna have too many threads, you're gonna, for example, hit the input-output bottleneck of the hard drive. But if you got too few threads, you will get your CPU saturated quickly. And same with workload. If you have a low workload, you end up with a low response time, which is good, but you will have a low throughput, which is bad. And if you will receive too many requests per second for your web server, you're going to end up with a high throughput, but with a miserable response time. So in fact, answering this question in practice, it's a really hard thing to do. Because as I said, that the answer depends on the configuration of the system. It depends on the architecture of the program, something that we cannot really control. But it also depends on the parameters of the hardware. It depends on the characteristics of the workload. And it definitely depends on the configuration of the web server. A good solution to this would be building a performance model of the system. Hopefully you can do it fast and with a minimal effort. So this performance model, it should predict the performance of the system, the performance of your web server for a wide range of configurations here. And it will act as an oracle. So you can use this model to, for example, deploy your web server automatically, to ask what-if questions about its performance, maybe to detect some performance anomalies in it. So it's really convenient. So with regard to approaches that people take nowadays to performance modeling, so in general, you can say that modeling the performance is trying to find out the dependency between the configuration and performance of the system. In some cases, people, they try to, to model this analytically. So this requires strong mathematical skills, good understanding of the system, which rarely coexist in developers. And analytic models is just a set of equations. What might not be good about it, it's if you have a very large, very, very complex program with a very complex behavior, it might not be that good at capturing its details of each behavior. Another approach is statistical models. When you just run your program in many different configurations, record performance for each configuration, and try to approximate it with like a neural network or nonlinear regression. So this is better. You don't need to know about your internals of your system, but you have to run the system in many different configurations, which might not be possible in production environment. So the ultimately good approach to this would be to build a structural model of the system, a simulation model of the system, which would try to replicate the structure of the system in its behavior. What it can be, a simple example of such model is a queuing network, right? You're trying to, to replicate the structure of your system in the structure of your queuing model. There are other frameworks for this, like a PACE framework, Palladio component models, and so on. So the good thing about these models is that they are very flexible. They can represent a really complex behavior and the structure of the system, but they're really hard to build. You have to know the details of your system fairly well. You have to know the source demands of your program. And as a consequence, most of the simulation models that are built currently, most of approaches to automatic building of these simulation models, they are done for modeling of message passing systems. And if you will try to apply this message passing system model, if you try to, to build just a model of web server or some scientific computing application which relies on logs, which relies on multiple threads and has some thread interactions, you will have a suboptimal performance. Like, for example, here people didn't take into account the synchronization operations in the system, and they got a 50% error. So our contribution is a simulation-based performance model for multi-threaded programs, which is specifically designed to take into account synchronization and concurrent resource usage. And we predict performance across multiple configurations with a high degree of accuracy, and we build these models automatically. Oops, I'm sorry. So now I will define the structure of a model, how it looks like, and what is due. So for the purpose of the modeling, we represent computation, we represent our program as request processing. So it naturally suits modeling of servers, interactive programs, but it also allows us simulating a wider range of applications like scientific computation applications, financial applications, because they can also be represented as this request processing system. We developed a 3-tier discrete event model for simulating these programs. So at the high level, we simulate the flow of the request through the program. At the middle level, we simulate delays that occur in the program working threads. And at the lowest level of our model, we simulate hardware and logs, which exist in the program. So the high-level model, it's essentially a modified queuing model, some flavor of the queuing model. So it simulates the request flow through the program as the program processes this request. So here in this model, queues, they correspond to the buffers and queues that are present in the program. And service nodes of the queuing system, they represent the program working threads. For example, here you might have a model of a web server which have an accept thread which accepts incoming connections. And connections are put in the queue, and then one of the working threads, it picks up those connections and processes them. One important aspect when we are talking about multi-threaded programs is the notion of thread pool. So thread pool is the set of threads which have the same functionality and can process requests in parallel. And they're important because the size of the thread pool, it becomes one important factor, one of the most important factors which affects the performance of multi-threaded program. So usually this is an important factor in the configuration of a multi-threaded program. It's an important configuration parameter. So as I said, that this is one factor that affects how fast the program can process requests. namely how many service nodes you might have in your queuing model, right? So the more nodes you have in perspective, the faster you can process requests. Another factor which affects the performance of the multi-threaded program is how fast these threads can process requests. Does it really take a long time, or they can do it really fast? Obviously. Any questions so far?
There are quite a lot of other things, like do these threads experience contention when they're accessing some shared
Absolutely.
resource? And so many, this list is incomplete.
Yes, this list is incomplete, and this is where I'm talking just about high-level queuing model at the 10,000 feet overview. But you're absolutely right. The question is also, when we will talk about like how fast the program is processing requests, the question is what this program is doing inside. What is the behavior? What are the computations that are performed by the threads? And this is what we simulate with the mid-level model. So mid-level models, they simulate computations which are performed by working threads. And we simulate those as probabilistic call graphs. So they essentially capture the call graph of the thread. Vertices of these models, of these graphs, they represent pieces of code. We call them code fragments. They represent pieces of code in the thread. And edges, they actually correspond, they represent the request flow, in which sequence these code fragments, they're going to be executed. So here we simulate request flow probabilistically. So say after executing this code fragment, this piece of code, the program can, with a probability of 0.7, engage in a, say, disk I/O, or it can go directly and try to say, access a lock or a queue. So we simulate these computations in a thread probabilistically.
What's the little green box at the bottom there?
So here it's just an icon for lock. I will come to it in a second. Mm-hmm. So now I just wanted to give you an example. What are the code fragments? So as I said, that we split the code of the thread into these pieces, code fragments. What are the code fragments? So the code fragment is a continuous piece of code in a program which performs one specific activity. That it performs either computations or input-output, like disk reads, synchronization operations, or reading and writing requests to the queues of the program. So in essence, we say that these types of code fragments, they represent the different sources of delay. What can cause the delay, request processing delay in the multi-threaded program? So just for an example, here's an example of a simple program which sort of tries to compare images. So it reads request. So it acquires the lock. It reads an image from the file. Then it gets another, say, image from the queue, compares this, reads another image from the file, compares these images, and puts the request back into the queue. So like some part of this request processing queuing program. So the code fragments here you can find here. So when you are acquiring the lock here, it's a synchronization code fragment. So this is a piece of code that is doing exactly synchronization. Then,
what about releasing the lock? Is that another one?
Yes. Then, once you acquire the lock, you read something from the file. You have a disk I/O operation. So this is, in the model, this is represented by the input-output code fragment. Next, when you are done, releasing the lock, it's another synchronization code fragment. So there are two different ones. Correspondingly, getting the request from the queue, this is what we call an in code fragment, which corresponds to accessing the queue in the high-level model. This is another read code fragment. It's another input-output operation. Then we are doing image comparison, which is a CPU-intense operation. It's represented by the computation code fragment. And finally, we push the result in the queue, which is another queuing operation. It's an output code fragment. So this is an example of programs and how we can divide it in code fragments. And this is correspondingly going to be the probabilistic call graph for this program. And this is going to be a very simple straight line. Any questions?
How do you deal with asynchronous I/O?
Asynchronous I/O?
Yeah.
So right now we are working on this. For some cases, what we can find, like in Java, you can represent it as a synchronous I/O. But it might be in certain in other cases you might have to handle it in a different way. So with regards to performance factors, what can, from the standpoint of this mid-level thread model, obviously the factors that determine how fast the thread can process requests, one factor is the structure of the call graph. Which code fragments are present here, which computations are performed, and in which order they're performed. Like if you have a loop, like for example, reading many times from a hard drive, it's definitely going to take time. So this is one factor. Another factor is how much time these particular code fragments, how much time they need to execute. So in terms of the model, we say that execution of each of those code fragments, it introduces some delay in the system. And what is this amount of delay? It can really different because of resource contention. Like if you have multiple threads accessing the same hardware resource as the CPU, you might start getting contention between them. The execution time will start growing, right? If you will have many more working threads than the number of available CPU cores. So the same about locks. If you have multiple locks, multiple threads competing for a lock, it will become more and more time. They will require more and more time to acquire that lock. So the execution time for this code fragment, for example here, which represents acquiring the mutex, it will also start increasing, right? So from the standpoint of modeling, this means that we must simulate locks and hardware in the multi-threaded system. And this is exactly what we do with the lower-level model. So our lower-level model, it simulates locks and hardware. It does it in the following way. So instead of explicitly specifying execution time for each code fragment, we rather specify parameters. Maybe it's a resource demand for a CPU code fragment or for a disk I/O code fragment. So these constitute parameters of the code fragment. And when the code fragment, when we execute it, when the model needs to know how much time it's going to take, it gets these parameters, it sends them to the corresponding low-level model. And low-level model, it sort of tracks the state of the system, contention of these locks, and based on this, based on the parameters, based on the resource demands of the thread, and based on the state of the system, the low-level model, it computes the delay. What is the delay necessary for this code fragment to execute?
So does this mean that you can then simulate thread pools that dynamically increase the number of threads in the pool?
In principle, yes. Okay. This definitely allows this. So this, I believe, it's quite flexible thing to, to model. Any other questions so far about the structure of the model?
When you have a lock, if you were to model the contention on the lock, you need to know which lock it is. Just to say it's a green box doesn't tell you enough.
Absolutely, absolutely.
And that might itself be hard. If you just look at the source code, you say it's called LOCK. That doesn't help me know when it's the same one.
This is what I'm going to tell you in the next slide. Any other problems? Yes, any other questions?
Are you modeling the CPU scheduler as well?
Yes, we do.
Okay.
So this is in fact part of this model. CPU scheduler, IO scheduler, we have simple models for that, yes?
So how are the three models related to each other?
So they form a hierarchy.
Okay.
At the higher level, you have this model of unit system, high-level model. The high-level model, it calls, when it works, it calls the model of working threads. And when the model of working threads work, during its work, it calls the models of the hardware. So it's like strictly hierarchical system. So if you don't mind, I will move forward because I have to finish a little bit earlier today. So with regards to model building, just as you said, you're absolutely right. In order to model locks, you have to know what the locks are. So initially, we did it manually, like trying to build those models manually. And it quickly became obvious that it's not practical. You have to scan the source code of the program. You have to understand it. It just takes lots of time. It's very error-prone. So it's obvious that in order these models to become practical, we need some automated solution. But automatic modeling is very difficult because it needs information about program semantics, and information must be retrieved from the program itself in the ideal case. Not from the developer, not from anyone else, but from the program itself. So now I will shift to the next part of my talk, which is about automated model building, how we can do this automatically. So in order to build this model automatically, we need following pieces of information. We need information about threads and threads pools, which are presented in the program. We need information about how these threads communicate with each other through queues. So we need list of queues, and we need list of these in and out code fragments in a program that access those queues. We need semantics of synchronization, which means we need to know about all the logs in a program, their types, and about synchronization code fragments, which represent synchronization operations performed on these logs by threads. And we definitely need information about computations and I/O, these code fragments, and we need to restore the structure of this call graph, how this works all together. So probably the hardest part here is finding the semantics of parallelism. What are the logs? What are the queues in the program? How threads are using those logs and queues? So in a general case, it can be a very difficult problem because you might implement these logs in a myriad of ways. You can, for example, use like low-level constructs, like in Java, these critical sections or synchronized sections and monitors, or you can use some high-level libraries for that. So we figured out that this problem is becoming much easier if the program uses a specific implementation of logs, a specific library that implements logs. Like Java util concurrent in Java, or system threading in a beloved C#, or some other library which provides implementation of logs. Just, for example, why it simplifies things. Let's just take a look at the Java program. So in a Java program which utilizes Java util concurrent, logs and queues are just instances of Java util concurrent classes. And you can infer the type of the log, like is it a semaphore, or is it a barrier, or whatever. You can infer it just by looking at the class name. And with regard to the synchronization and in and out code fragments, which represent calls to queues, you can just detect them by looking at the method names, because these operations are methods on the corresponding Java util concurrent classes, for example. And parameters of these operations you can also infer by values of arguments which are passed to those methods. And again, if you will take another library, there will be also other way to, for example, in system threading, I believe that it's the same approach. In Boost, it's very similar. So you can just by sort of looking at the specific implementation of logs, you can get all this information from the program by static and dynamic analysis, which with high degree of accuracy.
To know about contention, though, you need to do alias analysis, don't you? To know about contention.
What?
To know about lock contention,
yeah.
You need to know when two variables refer to the same value.
Yeah.
So that's not sort of more analysis to be done. Like alias analysis.
We look at with our implementation in Java, we look at the reference to the Java object. So in Java, for example, every object can be identified by ID. So yes, you have to do alias analysis, and we are doing this. Yeah, essentially we do. So with regard to steps for building model, our methodology, it involves 3 distinct steps for model building. So first of all, we run the program sample its stack and detect thread pools in it. Then we scan the source code of the program and discover code fragments in this source code. Then finally, during the third step, it's the dynamic analysis. We instrument the program, run it in a specific configuration, and get all the rest of information from the model trace. So I will briefly touch all these steps. So the first steps is the thread pool detection. Here we detect what are the thread pools in a program and what can be the size of these thread pools. So we rely on the observation that usually threads from the same thread pool, they execute same methods. And so what we do, we take snapshots of the program as it runs. We get the structure of the call trie for this program, which methods are called. And for each method, we record a set of threads, a tuple of threads which executed. And frequently encountered thread tuples, like here, for example, you can see pattern that, for example, these methods, they are executed by thread 1. These methods, they are executed by thread 2 and 3. And these methods, they are executed by threads 4 and 5. So these are essentially thread pools represented that are present in a program. So so this is like an overall approach to thread pool detection. In fact, we're doing much filtering, but in essence, this is how it works. So with regard to, so once we're done detecting thread pools, we are doing static analysis, during which we detect code fragments. So we analyze the source code of the program and track specific constructs in it. So, for example, calls to the program logs, as it's shown here, as I said, these are becoming synchronization code fragments in our model. And calls to the program queues, these ones are becoming in and out code fragments. We also track initialization, construction of these logs and queues. Because in this sense, by looking at those constructors, we can essentially infer what are the logs present in the program.
How do you know that it is a queue? Are you again assuming that you use some standard library whose names you know?
Currently, we're assuming this. Because otherwise, detecting of queues can be a big topic on its own.
Indeed.
Yes. My advisor also did, and this is a whole different, separate can of worms we can open. So this is how you detect these logs and queuing operation during the static analysis. We also detect the input-output operations here. In this case, we track calls to certain functions and methods which can access the hard drive, which we track both calls that can access the system metadata and that can actually do file I/O operations. And then once we detect all of those, we instrument the program and by inserting probes on the boundaries of these code fragments. So code fragments, so these probes, each probe is identified by identify, a separate ID, and we use this pair of IDs to identify particular code fragments here. So when the program runs, it generates a trace. So the trace includes the number, the ID of the probe which has been executed, the time when it was executed, and also additional information which is used to establish the logs and queues in the program and their parameters. So in this trace, the code fragments, they are represented as coincident probe hits, like here. So these are sort of overlap in the trace. So those code fragments that we knew from the static analysis, these correspond to code fragments to synchronization operations, to hard drive I/O operations, and to queue accesses. And all the code fragments that reside between those, they represent computations. So we don't explicitly track computations during the static analysis, but we detect them in the dynamic analysis here. The trace also provides us parameters of code fragments. So, for example, tracking the calls to constructors and initializers of logs and queues, it allows us to establish parameters of logs. For example, here you created a semaphore with number of permits equal to 4. And this initializer, by looking at the value which is returned by this constructor, we can get the log ID, for example. So this is log resolution, right? It's implemented in this way. And every time you see a call to this particular log, you can establish that this log corresponds to this particular semaphore, for example. And correspondingly, if this synchronization operation involves certain parameters like timeout, these parameters, they will also appear in the trace. So we can get it from the trace as well. With regards to other types of code fragments, like CPU code fragments and input-output code fragments, we also retrieve their parameters from the trace. Like for CPU, it's easier. It's like the amount of CPU time which requires the code fragment to execute. For input-output code fragments, it's a little bit harder because for those, parameters of those are sequence of low-level hard drive accesses performed by that particular code fragment. And those we can retrieve in kernel mode only. But we essentially, in our work, we use the cross-correlation to match these kernel mode operations to I/O mode, to user mode I/O operations, and get the parameters of I/O code fragments. One last step that we need to do is to reconstruct the structure of the call graph. So we do this by just tracking, like, for example, this particular code fragment S1. We track which code fragments were ever executed in the trace after this particular code fragment. And this gives us both the structure of the call graph, and by looking at the execution counts, you can infer the probabilities of transition from one code fragment to another, and this gives us the labeling for a code graph, the probabilities. So this was more like a high-level overview of what we've done. In fact, this detection, this automated model building is a much more complex problem. And it requires additional steps, additional cleanup. For example, you need to address the bloat of the code graph, of the call graph. If you do it in this sort of plain form, you will end up with a very large, unreadable, unrecognizable model. You may, for example, need to look in the libraries of the program because you have to represent them separately in a sort of, you have to address them as you build the call graph. But if you have any questions about this, I will happily speak about it offline. Just because of lack of time, I cannot go into deep details now. So this was about automated model generation. Do you have any questions about this part?
You said that you're looking at the source code on the one hand, and you're generating dynamic traces on the other.
Mm-hmm.
Right? So, and in your previous slide, you had something about, well, we could know the lock ID.
Yeah.
Right? But of course, the same source line might access many different locks if you're walking over a tree and locking every node, say. Right. So there isn't a simple one-to-one correspondence of
no, it's not simple
lock
one-to-one.
ID to program source code, is
Yeah.
there?
So in this case, you can.
It's quite hard.
Yes, it can be hard. So one approach to look at this is to, again, probabilistically, that you can, with certain probability, access, like this particular code fragment, it might, with a certain probability, access lock. Another approach is to try to establish some determinism. We do establish some determinism in the program by a certain degree, not for this case, but yes, this is some case that might be taken into account.
So what do you actually do?
Probabilistically.
You do something called that.
Yes, so we sort of like probabilistically try to, to say that there is a certain probability of calling this particular lock.
Okay.
Mm-hmm.
So if you're executing the thing and probing, what data are you using? Because, for example, the lock problem is completely different. If you're working in a small data set and locking each element, then you have high lock contention.
Yeah.
And if you have a very large one, it's completely different. So what data are you using for that?
For what? Excuse me.
So for the dynamic execution, where you extract information. I mean,
What's your workload, he's asking?
Yeah.
So it really depends on the structure of the program. Like looking ahead for the programs that we looked at, the overhead was typically under 10% with regard to execution time. Is this like what you're asking?
No, what data are you using when you're executing it for your probing?
The workload for the program.
Yes.
So in fact, we are trying to, like for this part, we did like for the web server, for example, we just send the request to the web server, to the instrumented web server, and then the instrumented web server just, when it runs, so it just gives you the trace of locks. And the same, regardless of the workload, regardless of the type of the program, the sort of the general idea, the structure of this instrumentation, it remains the same.
Are there not standard benchmarks for testing web servers? Workloads for web servers?
So right now we used synthetic. So we used two, like speaking of evaluation, we mostly use like a Wikipedia dataset to host our web server, and we tried to generate requests randomly to that. So we didn't use any standard benchmark. So essence, the type of the benchmark, it will correspond in terms of our model to slightly different call graphs and to slightly different resource demands. So I will talk about evaluation in a second, if you don't mind. So if you have any questions, I will be happy to answer to them. But if you don't mind, I will just shift to the evaluation part now. So with regard to our work, our primary concern was the accuracy of the model. So we tried we measured the accuracy in the following way. We built the model using one configuration of the program, like one combination of working threads and the workload in the case of a web server. We used this configuration to build the model. Then we ran the program in many other configurations. We ran the model in the same number of configurations. And for each configuration, we recorded the predicted and actual performance. We compared them. We calculated the relative error. Hopefully, for a good program, for a good model, the relative error should be minimal. In this case, we can say that the model predicts the behavior, predicts the performance of the system with a high degree of accuracy.
So was this the same workload, and you changed the configuration, or you train with a different workload?
So the structure of the workload was same. Like the probabilities of accessing web pages was the same. Addressing the different shifts in the workload, it's a part of our future work that I hope to work on. The intensity of the workloads, the number of requests per second, was different. So it was one of the configuration parameters. But speaking forward.
So are you going to tell us what the configuration parameters were? Okay.
So with regard to the test programs, I mean, we tried a couple of those. Here I want to concentrate on large industrial programs that we tried to model. It's a Sunflow, which is a 3D renderer that parallelizes the rendering across the pool of working threads. And this is an Apache Tomcat, which is a large complex web server and a servlet container. For Tomcat, we built two models for two distinct configurations of the Tomcat. One of them was the model of the web server. In this configuration, Tomcat was just employed as a regular web server to host a number of static web pages. It's a disk I/O bound workload. And the other configuration was a servlet container. It's a CPU bound workload, in which case the Tomcat, it was generating a PDF documents, which is CPU bound operation. So these are medium to large programs. For example, Tomcat, it's 200 to 300,000 lines of code. The number of probes, it depends on the size of the program. For the Sunflow, it was about 400 probes. For the Tomcat, it was close to 4,000. So with regard to execution time, the overhead was from 2 to 7%. And in general, our model, it runs in general from 10 to 1,000 times faster than the actual program. The overall speed up, it ranges from, it can really depend on the structure of the program. Also, for this study, we're mostly concerned on the accuracy and validity of the model, and speed up can be increased in future significantly. So with the hardware configuration, we ran this on a pretty much a commercial hardware. Is a quad-core CPU system, 4 GB of RAM. So these are results. For the Sunflow, the configuration parameters that we tried to take into account in our study was the number of active CPU cores that were available to the system. So we ranged it from 1 core to 4 core system to see how programs respond to this. And the number of working threads which the web server had. So as you see, this test, it really tells you that here the actual performance, by the way, is showed in red, and the predicted performance showed in blue. And these charts, they compare how actual performance is close to the predicted one. And by the way, the error bars here, they show the standard deviation across the whole run.
So this is an example where you've just essentially got almost linear speed up, is that right?
Yes, so this is easy indeed. Yeah. So this program is, in terms of parallelism, in terms of high levels parallelism, it's perfectly parallelizable, almost perfectly parallelizable. So, but I would say that the important part here is that this was generated automatically. So the model was, our framework was be able to, to parse through this program, to capture all the semantics of synchronization, and to translate into a valid model which was quite accurate in predicting the performance of the program. So with the Tomcat, this is probably a much larger program with a more complex behavior. So here the parameters, the configuration parameters for Tomcat was the number of working threads for the system again. And the workload, the intensity of the workload, how many requests per second the web server was receiving. And here, as you say, that we are pretty well predicting not just the mean, the average response time, but also the range, the sort of the variance in response time that the server has in this particular setup. And with the throughput, I would say this is a very good thing that we accurately predict the point of saturation here. So at this point, the server reaches the saturation point, and this is what you probably would care about, would really concern if you deploy it in an industry. Yes?
If you did a simple analytic model, say a simple queuing model, how much better or worse would that be than the simulation?
First of all, before getting the simple analytic model, you would need to get the resource demands of the system, right? So this is one thing. With the analytic model, it's hard to say. Honestly, we didn't do this study. So here, the next part is the running the web server in a IO-bound setup. So here, what is interesting here is that some part of the resource demands of the web server, it's IO, it's disk IO, but some part is the CPU demand. So for example, for here again, the parameters are the workload intensity and number of working threads. Like here, if you would compare 1 working thread and 4 working threads, you will see that the performance here have increased because about the quarter of the work the server is doing, it's the CPU activities. And here you have one hard drive, which it won't give you a speed up when the number of working threads increases. But this CPU part of the workload, you can parallelize it across cores. And in this case, the model correctly captures that there will be some speed up due to the CPU cores. And I would say, in this case, capturing this type of behavior with a simple queuing model, it would be probably harder. Because, by the way, with the queuing model, with the classic queuing model, you will assume that in many of those that the resource demand, the service time by the service node is the same, right?
And it's not?
And the resource demands, the service time. The service time, certainly it will be like when you have this hard drive problem, when you will increase the number of working threads, you will end up with a bottleneck on the side of the hard drive, right? So for each of those threads, the service time by the program threads, it will start increasing. In essence, more or less proportionally to the number of working threads because of the contention. So with classic queuing model, you can hardly simulate this because the processing time, by the thread, it will be different across configurations. So this is the throughput for the web server, which is, again, we are sort of good in predicting the saturation point, which can be, as you see, it's quite different across the number of working threads. And a part of this, as I said, that we tried our approach, we tried it with a different number with the different programs, and we also got decent results here, but I can't show it here because of lack of time. So with regard to comparison to other systems, it's really hard to compare because there are so many different programs and different types of programs and different types of models. But still, we are sort of somewhere in the middle. So we are still sort of correspond to the state of the art. So I would say that to summarize this a little bit, I would say that the contribution of this study is that the model was particularly developed to simulate multi-threaded applications. These models are built automatically for large, complex industrial applications, and they were able to accurately predict performance in a variety of configurations. So from findings of this research, I would say that to simulate the multi-threaded systems accurately, you definitely need to model log behavior and hardware behavior. And accurate data collection is very important here. For example, here in the Tomcat, like 10% error in collecting the parameters, resource demands here, it would correspond to 90% prediction error here. So this is something that we quickly figured out, that the accuracy of data collection is very, very important here. That in order to be useful, models must be simple and compact, that's for sure. And another thing that we also become aware is that debugging of performance model is very hard. It's very untrivial thing to do, so maybe there is some area to research to look at debugging of these models in particular. So as I say, that currently we have a number of assumptions on the program. That with regard to generation, to model generation, we assume that the model has standard implementation of locks and queues, some sort of library. We also assume that the workload characteristics, like the probabilities of hitting a particular web page, it doesn't really change in time. That there is nothing significant running in parallel, like you don't have two programs deployed on the same machine. It's more like a limitation of current implementation, but not a principal limitation. And the hardware doesn't really change between configuration. As we say that we tried with a different number of CPU cores, but you cannot really simply take it from one machine, apply it to another on a separate memory architecture, and you will get accurate prediction. So we are aware of these limitations, and we want to address them in a future work. So the main goal of our future work is to develop a more flexible approach to modeling, which can allow us to simulate a more wide range of programs and workloads, because in this study we were mostly concerned about the accuracy. Now we want to make this more broad. So first thing that we are doing and we're trying to do with my advisor Steve Race is to infer semantics of complex log, like which were built from the low-level primitives like queues and semaphores and so on. So there was a preliminary paper on this published. Second, we also really want to address the changes on the workload. So we will either update the model parameters online from the running program or employ a hybrid of discrete event and statistical model. We want to address changes in hardware. And one particular thing that we want to address is to see how changes in the program itself, how they affect the performance. So this, I would say, it's an interesting problem that we want to look at, because it would set the criteria for model reconstruction. Another approach to make this model more flexible is to shift from this completely automatic approach that we have now to more automated modeling. Like one approach is think of design for simulation, like in which way you want to design your multi-threaded program so it would be easy to understand. So you could easily understand in performance, maybe easily simulate it. How you can do this and what can be the trade-offs here? How much, for example, the performance impact you might have? Another approach for automated modeling is to use some user input. That the developer or analyst might annotate the key constructs in the code of the program, like queue accesses, locks, like say that this particular class corresponds to semaphore, for example. So to guide this model generator, automatic model generator, what it is.
Could you pick up assertions right now in your analysis?
To some extent, yes. Okay. Yeah. And more broad vision, like what we can do here in this area, is again to apply this principle that we've developed for building these models to different applications. Like, for example, we are now predicting performance of the system. We want more to understand what is causing the performance degradation, for example. We want to visualize these performance models. We want to visualize this application in a programmer's terms, visualize its performance aspects in a programmer's terms, like where the programmer should look at in the program. What are the possible improvements to this program? Also, maybe it's a different interesting problem is like you have a particular program. What might be a good hardware to run it? Is it like an AMD-oriented thing, or maybe you should run it on Intel with a different memory architecture, with a slightly different CPU architecture? And definitely we want to apply this to new types of systems. like hybrid programs that do both CPU and GPU computation, and for mobile offloading, when you offload something from your cell phone to the cloud to save some energy, and how this is going to affect the overall performance of such system. So these were some publications here that we produced in the process. And if you have any questions, I will be happy. Any more questions, I will be happy to take those now.
Yeah. So are there any more questions?
You mentioned memory contention or cache contention.
So right now, yes. Right now, we simulate all memory as computations. So we are aware that there is some problems, especially for scientific applications, probably for HPC systems, for massively parallel systems. So this is indeed one of the things that we want to look at. It's like changes in, we want to address it as one of our future works, maybe in a hardware section. Developing compact and fast models for memory and cache.
Peter, did you have a question?
Yeah, question just about aggregation. Have you looked at the trade-off between speed and accuracy if you start aggregating your models into larger blocks? Your model would lend itself to essentially coalescing nodes. Have you?
You mean the speed of model or overhead?
The accuracy of the model compared to the size of the model, essentially the complexity.
Mm-hmm. Good question. So in fact, we did some optimization, heavily optimization on the as I say that in many cases you might end up with a very large model. So we tried to, we did all our best to make the model more compact without the loss of accuracy. So we did it in a couple of ways. First of all, we tried to get to the phases of the system. That in certain cases the system is maybe not processing requests at this particular stage, so we are not simulating this stage, or generate a simplistic model for this stage. And also we detect those code fragments, those operations that have a marginal, if any, impact on the performance, and we are sort of skipping those elements of the program from modeling altogether. So all those results that I presented you here, these models underwent this reduction, and it helped to reduce the size of our model by orders of magnitude. Does it answer your question?
I wanted to ask, you have these 3 levels in your hierarchical model. Can you give us some intuition as to which one, how much of your accuracy comes from each of the models? What would happen if you only had the top model? What would happen if you only had the top and middle layers in your model? How would these affect your performance prediction?
Okay. So with regard to without the middle model, as I say, that the model would just sort of fall apart. If you would assume the same execution time regardless of, say, the number of working threads, which is essentially the number of nodes in the high-level model. You will have probably a plain line here.
Okay. Apart from the number of working threads, what other configuration parameters have you evaluated?
So right now we evaluated the CPU core count. That's one thing that we evaluated. The workload, intensity of the workload for the web server. We also looked at the system-wide parameters, like the possible number of file descriptors that the program is allowed to have, so how this affects the performance of the model. We had some work on that. So these are main parameters that we looked at. And by the way, with regard to the low-level model, again, if you want to simulate the contention, you might end up with a straight line from here to here. So these 3 parts of the model, they are sort of integral. They are very important for each other. You cannot really just throw it out if you are talking about the multi-threaded system, resource contention.
Simon.
If you've got, as I understand it, your thread pool, you identify the thread pools by saying, I look at runtime and I see that they're executing similar work. Mm-hmm. Is that right? But not all thread pools do that. Some of them just take lists of work items from a work list and run them. like something that's servicing an F-sharp.
Producer-consumer architecture, right? Are you talking about a producer-consumer architecture?
No, just something where the thread pool simply services some kind of work list of jobs to be done that might be, coming from different parts of the program.
So in this case, I mean,
virtual CPUs, if you like.
yeah, but still, if you will, so here in this approach, we look at the aggregate performance of the system. So you are supposed to observe it for some amount of time to sort of to get the average, like high-level view of it. So essentially, this will average out like statistically.
Yes, I think we are out of
we can
time.
definitely talk about it more. I mean, I can talk much more about this thread pool detection. I have slides for it. But I'm here for the next 2 days. So.
Okay, we need to thank the speaker again because we need to get on to the next talk. Thank you.